Okay, 2072. We have a non-conducting solid sphere, radius A, with charge positive Q uniformly distributed. So what they're saying is that rho is uniform, but they don't give us rho, which means that our final answer needs to have Q in it, not rho. Okay. Throughout its volume, it's concentric with the non-conducting spherical shell of inner radius 2A, outer radius 3A, has negative Q uniformly distributed. Okay, we need to express all answers in terms of the given quantities and fundamental constants. So using Gauss's law, we want to derive expressions for the magnitude of the electric field as a function of radius r in the following regions. So r less than a, r greater than a, less than 2a, and so on. Okay. So let's start with the first one, and we will draw a Gaussian surface that is less than a. All right, so I'm just gonna. That's not good. I'm just gonna copy this over each time, each part. Okay, so part 1. Okay, so the first thing we need to do is we need to pick a Gaussian surface, and this Gaussian surface needs to be in between, or at least less than a, I should say, and it'll have radius of r. Radius of r. Okay. So Gauss's law, closed integral E dot dA equals Q enclosed over epsilon naught. Okay, it doesn't contain all of the positive Q charge, so we can't just put positive Q over epsilon naught. We need to figure out what proportion does it contain. Okay, the left side, let's just do the left side first because it's always going to be either 0 or E times A. So the left side will be E times the area of the Gaussian surface, or E times 4 pi little r squared. So easy enough for the left side. The right side, we need to use the fact that the charge is uniformly distributed. Okay, so what that means is that rho, which is charge per volume, is constant. Okay, it's a constant. And so what that means is that rho is equal to the little charge, the amount of charge enclosed divided by the volume. Okay, the amount of charge enclosed is this volume right there, which is the volume of our Gaussian surface. Okay, so volume of the Gaussian surface, and that equals the total charge, so total charge is Q, divided by the total volume of that sphere. So Q enclosed is equal to Q times the volume of the Gaussian surface divided by volume, the total volume. So that's Q times a 4/3 pi little r cubed divided by 4/3 pi big, no, not big, A cubed. Right? Yep. Okay, the 4/3 pi's cancel. And so we get Q enclosed is equal to Q little r cubed over A cubed. Okay. And then we can, so that means that Q enclosed over epsilon naught is just Q r cubed over A cubed over epsilon naught. All right, so now we'll set the left side equal to the right side. So the left side was E 4 pi r squared. E 4 pi r squared is going to be equal to the right side. So Q r cubed over A cubed over epsilon naught. Okay, solving for E, we get Q, okay, 2 of those cancel 2 of those, so we're just left with 1. And we get Q r divided by 4 pi A cubed epsilon naught. Okay, so that's electric field when r is less than a. Part 2 is when, let's see, part 2 is when R is in between A and 2A. Okay. All right, so when R is in between A and 2A. Okay, if I draw a Gaussian surface, that would be in this region right here. Oh, why can't I draw? There we go. In that region right there. We've done this a few times now. We know what the electric field is when you're outside of that of a sphere of charge. It looks just like a point charge. If you need to apply Gauss's law to convince yourself, go ahead and do that. But I know that the electric field is going to equal Q, all of that charge Q, over 4 pi r squared epsilon naught. And I'm not going to do anything else, where r is that radius right there. All right, part 3. Okay, so let's see, part 3. We want when r, let's see, when r is greater than 2a but less than 3a. Okay, so we want to pick a Gaussian surface, and we need it to be in this region right here. And it has radius of r. Okay, so applying Gauss's law, we have closed integral E dot dA equals Q enclosed over epsilon naught. Okay, the left side should look the same, E times 4 pi r squared. The right side is a little bit trickier. Okay, so how much charge does it contain? Notice that it contains this little bit of charge, and it contains this whole thing. Okay, so we have to be careful. That white area, there is no charge in that, so we can't count that volume, and we cannot count the gray area that I did not highlight. Okay, so Q enclosed, then, looking at this picture, is going to equal, it should equal all of the positive charge plus some of that negative charge from the outside conductor. So I'll call that, we don't know how much that is, I'll just call it Q, but let's just call it Q outer. Okay, we need to figure out what Q outer is. Okay, so let's do that. Okay, so Q outer then, again, it's uniformly distributed, the charges, so rho is a constant. Rho is going to be equal to the amount of charge that we want, Q outer, divided by that green piece of volume. Okay, so the volume we want is this part that I've highlighted. So that part that I've highlighted. So we have to be careful when we actually do that volume. So volume, we'll call it volume outer, which is equal to all of that outer shell charge, which is negative Q, divided by the total volume outside. Okay, so how do I figure out that volume? Notice that the total volume total, that is going to equal the volume of a sphere of radius 3a minus the volume of a sphere of radius 2a. Okay, so what the total volume would look like is a 4/3 pi times a 3a cubed minus a 4/3 pi times a 2a cubed. And then the volume outer, that highlighted piece, is going to be the volume of a sphere of radius r minus the volume of a sphere of radius 2a. So that one is going to look like this: 4/3 pi r cubed minus a 4/3 pi times a 2a cubed. 2a cubed. Okay, so let's put all of that stuff together. So q naught is going to be negative q v0 over vt, which is equal to negative q. We said the volume of the outer part that we want is 4/3. I'll factor out the 4/3 pi, and we have r cubed minus, let's see, we had r cubed minus 2a cubed, or we could say 8a cubed if we cube the 2. So 8a cubed. And then we will divide by a 4/3 pi times the volume total we said is a 3a cubed, or we could write that as 27a cubed, minus 2 cubed again is 8, so we have an 8a cubed. 8a cubed. Okay, the 4/3 pi's cancel out. We could do 27 minus 8 and get 19a cubed. Could replace that denominator like that, and we'll leave the numerator. Okay, so we get q outer is equal to a negative q. We have an r cubed minus an 8a cubed on top, divide by a 19a cubed on bottom. Okay, you could simplify this a little bit, but I suggest just leaving it like this and try not to, so that you don't make any mistakes simplifying. Let's just leave it like that. Okay, so that's what q outer is then. So that means that q enclosed is positive q minus q r cubed minus 8a cubed divided by 19a cubed. Okay, and then putting the left side and right side together, we are going to have e 4 pi little r squared equals q enclosed over epsilon naught, or q minus q r cubed minus 8a cubed over 19a cubed, and then we divide by epsilon naught. Okay, so solving for e, we're going to get q minus q times r cubed minus 8a cubed divided by 19a cubed over 4 pi r squared epsilon naught. Okay, could simplify this. The scoring guide for this problem looks a little bit different because they did simplify, but I would not risk simplifying any further than this. So I would just leave it like this. All right. Last part, right? No. Now we got to do, yeah, I guess that is the last part now. So part 4. So let's see. Here's our sphere. Okay, so for part 4, if we were to draw a Gaussian surface, it would be out here. Okay, and if we apply Gauss's law, we have closed integral E dot dA equals Q enclosed over epsilon naught. How much charge is enclosed? We have all of the positive Q minus the negative Q, or I guess plus the negative Q, which is going to be 0. So if Q enclosed is 0, that means that E is equal to 0 out there. Okay, and so we're done with all of part A.